Hi, welcome to part 6 of the video series about laws of motion. In this video, we are going to learn about the universal law of gravity and how it is related to the difference of the mass and weight of an object. One of the fundamental forces which has been involved in the creation of the universe is the force of gravity. It is maybe the weakest of all the fundamental forces, but it has played a crucial role in the creation of the universe. According to the universal law of gravity, each body in the universe attracts every other body with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Let's assume two objects of masses m1 and m2 respectively. Let's consider r as the distance between the centers of these two objects. Universal law of gravity states that the object with the mass m1 will attract the object of mass m2 with a force of F1 on 2. At the same time, the second object m2 will attract the first object m1 with a force of F2 on 1. These two forces are making together action-reaction pair. As we recall from the third law of motion, these two forces are equal in magnitude but opposite in direction. We can calculate these two forces by using the formula on the screen. As we can see, forces are directly proportional with the product of the masses and inversely proportional to the square of the distance between their centers. In the formula, we have one extra parameter or proportionality constant, uppercase G. G is the universal gravitational constant. Its value is same across all the universe and is equal to 6,67 times 10 power to minus 11 Newton meter square per kilogram square. Please don't confuse this big G with the smaller one, which is gravitational acceleration. According to the universal law of gravity, all objects in the universe are attracting each other. What about the objects in our room? According to our observations, some objects can remain in our room for years, but we have never observed them coming closer even by inches. Does it mean that universal law of gravity is wrong? To understand what is going on, let's see the formula in action. We are asked to calculate the force of gravity exerted by the object on the left on the object on the right. Both objects have mass of 1 kg and the distance between their centers is 1 meters. First, we write down the formula to calculate the force of gravity. Then, we substitute the values in the formula. G is 6,67 times 10 power to minus 11. Mass of each object is 1 kg and the distance r is also equal to 1 meters. As a result, force of gravity is equal to 6,67 times 10 power to minus 11. If we write it as a decimal number, we get the value on the screen. This is such a small number that even if there was no friction force preventing these objects from moving, it could take them millions of years to move a tiny distance. Force of gravity becomes more relevant if at least one of the objects has a huge mass. We can feel the effects of it on the objects on the surface of a planet. Any object we drop from a certain height is falling down. This is due to the gravitational force applied on this object by the planet. In an image on the screen, we have an object of mass small m on the surface of the planet with a mass of big M and radius of big R. By convention, if we have two objects with one of them with much greater mass than the other one, instead of using m1 and m2, we use big M for the mass of the heavier object and small m for the mass of the lighter object. Another convention is to use uppercase R for the radius of a planet. As the radius of the object is negligible compared to the radius of the planet, we can say that distance between the centers of the planet and object is equal to the radius of the planet. In this case, we can formulate the force of gravity as seen on the screen. Now, let's consider the following case. The object which is initially on the surface of the planet is now moving away from it to a significant height h. This time, the distance between the center of the planet and the object is not equal to the radius of the planet anymore. It is equal to the radius plus h, the height of the object above the surface of the planet. In this case, we have to adjust the denominator in the formula. In the video about the first law of motion, we have already learned that the mass is the quantity of a matter in a physical body, or it is the measurement of an inertia. On the other hand, weight is the force of gravity experienced by a body. Previously, we have learned that weight is equal to the product of the mass of an object and gravitational acceleration. Also, as you know, force of gravity can be calculated by using the formula on the right side of the equation. Each side of the equation has the mass of the object in it, which is represented by smaller m. We can get formula to calculate gravitational acceleration by cancelling small m in each of these two formulas. Gravitational acceleration is the acceleration of an object in free fall within a vacuum. In all our previous calculations, we were using 9.8 meters per second square as a value of g. But according to this formula, we can see that g actually is not a constant. It may vary depending on the values of the mass of the planet and its radius. It brings us to conclusion that weight of an object is also not a constant, as it depends on gravitational acceleration. Our mass is the same wherever we are, because the amount of the stuff we are made of doesn't change. Our weight depends on how strong a gravitational force is acting on us at that moment. On the table, we can see the comparison of the weights of the same object of mass 10 kg on different planets. The average gravitational acceleration on Earth is 9.8 meters per second square, and the weight is 98 newtons. We say average gravitational acceleration because even on the surface of the Earth, g is not constant. For example, it has greater value on the poles and smaller value on the equator. On Venus, weight of an object is slightly smaller than the one on Earth, 89 newtons, as the gravitational acceleration on it is 8.9 meters per second square. The object will be heaviest on Jupiter, as the gravitational acceleration on it is 23.1 meters per second square, and the weight is 231 newtons. A satellite orbits a planet at a height where the gravitational force is 1/9 of the force it experiences on the surface of the planet. If the radius of the planet is r, the height of the satellite above the surface of the planet is a 9 times r, b 8 times r, c 3 times r, d 2 times r. According to the definition of universal law of gravity, gravitational force is inversely proportional with the square of distance between the centers of these objects. To decrease the force 9 times, distance must increase 3 times, as square of 3 is equal to 9. Especially in multiple choice questions like this one, learners happy to see that the answer is in the options and immediately mark C as the correct answer. You must be aware that answer of 3r we have calculated is the ratio showing us how many times the total distance has increased. But the question is to calculate the height above the surface. When the satellite is on the surface of the planet, the distance r1 is equal to the radius of the planet. When the satellite orbits around the planet, it is a distance h from the surface. So distance r2 is equal to the sum of radius of the planet and the height h. After substituting r1 and r2 in the first equation, radius of the planet plus height is equal to 3 times the radius of the planet. As a result, the height is equal to 2 times radius of the planet. So the correct answer for this question is D. Let's see some more examples. We are asked to calculate the gravitational force applied on a 100 kg object by a hypothetical planet Z. Mass of the planet is 7.2 times 10 power to 20 kilograms, and the radius of the planet is 500 kilometers. Solutions for physics questions involving calculations must consist of 3 steps, as mark allocations are done accordingly. Usually, the first mark is allocated for the formula, the last mark is allocated for the answer. The rest of the marks are allocated for the substitutions. For all of the examples, we will try to follow the same structure. First, we write down the formula for the force of gravity. And then we do substitution. Universal gravitational force is 6 times 67 times 10 power to minus 11. Mass of the object is 100 kgs. Mass of the planet is 7.2 times 10 power to 20 kilograms. The radius of the planet is 500 kilometers, which has to be converted to meters. As an answer, weight of the object on planet Z is 19.21 newtons. In the second example, we are asked to calculate the gravitational acceleration on the surface of Jupiter. As we learned in the previous example, as a first step, we write down the formula. Gravitational acceleration is equal to universal gravitational constant multiplied by the mass of the planet divided by the square of the radius of the planet. Universal gravitational constant is 6.67 times 10 power to negative 11. Mass of Jupiter is 1898 times 10 power to 27. Radius of Jupiter is 71,492 kilometers, which has to be converted to meters by multiplying it by 1000. Gravitational acceleration on the surface of Jupiter is 24.79 meters per second square. In the last example of this video, we are going to calculate the mass for a hypothetical planet with gravitational acceleration of 4 meters per second square. We start the solution by typing the formula for gravitational acceleration, as its value is already given in the question. Value of gravitational acceleration is 4 meters per second square. Universal gravitational constant is 6.67 times 10 power to minus 11. And the radius of the planet is 600 kilometers, or 600 times 10 power to 3 meters. The only missing value in this equation is mass of the planet. After calculation, mass of the planet is equal to 2.16 times 10 power to 22 kilograms. We are asked to calculate the difference in the weight of a climber at the top of a mountain and at a ground level. Mass of the climber is 80 kgs, and the height of the mountain is 5,000 meters. The question also provides us with all the constants required in our calculations. To calculate the difference of weights, first we need to calculate the weight of the climber on the ground and then at the top of the mountain, and then subtract these two values. Let's start with the weight of the climber on the ground level. If an object is on the ground level, as a distance we use the radius of Earth. There is an easy method of calculating the weight of an object on the surface of Earth, but we will see it in the next question. For this question, let's use the formula for the force of gravity in order to see both methods in action. The next step is making substitutions. Universal gravitational constant is 6.67 times 10 power to negative 11. Mass of the climber is 80 kgs. Mass of the Earth is 5.98 times 10 power to 24. And the radius of Earth is 6.38 times 10 power to 6. Weight of the climber on the ground level is 783.93 newtons. Now let's calculate the weight of the climber at the top of the mountain. Unlike the previous case, if a climber is at the top of the mountain, the distance between Earth and the climber will be equal to the sum of the radius of Earth and height of the mountain. In this case, the denominator in the formula of the gravitational force will become r plus h squared. We can proceed with substitutions, but don't forget to add 5000 inside the parentheses in the denominator. Weight of the climber at the top of the mountain is 782.7 newtons. Let's recall the values of weights. Weight on the ground is 783.97 newtons and weight at the top of the mountain is 782.7 newtons. The task was to calculate the difference of these weights. 783.97 minus 782.7 is equal to 1.23 newtons. Even though the next question is slightly challenging than the one we have just solved, the solution will be very similar. According to this question, there is 19% difference in the weights of an object on the surface of the Earth and while orbiting Earth. Our task is to calculate the height h from the Earth's surface at which the satellite is orbiting. Mass of the satellite is 300 kgs. As in the previous question, to solve this one, we will try to split the solution into two parts. First part is then the object is on the surface, and the second part is when the object is orbiting the Earth. As we mentioned before, there is an easy way to calculate the weight of an object while it is on the surface of Earth, and we have already used this method in a lot of previous questions. Weight of an object is equal to mass times gravitational acceleration. Of course, we could use the formula for the gravitational force as well, and the answer was going to be slightly different, since 9,8 is the rounded value for gravitational acceleration. But in the memos of exam papers, both solutions and answers are getting you full mark. 300 multiplied by 9,8 is equal to 2,940 newtons. Now let's calculate the weight while the object is orbiting around Earth. In this question, it is given that the weight while orbiting is 19% less than the weight on the surface. Initially, the weight was 100%. Now it is 19% smaller. 100% minus 19% is equal to 81%. We have calculated the weight of the satellite on the surface as 2,940 newtons. Weight of the object on the orbit is 2,381.4 newtons. Once we know the value of the gravitational force, we can use it in the formula. Let's make sure that we don't forget to add the height in the denominator. Weight is 2,381.4. Mass of the object is 300 kgs. Mass of the Earth is 5.98 times 10 power to 24. And finally, the radius of Earth is 6.38 times 10 power to 6 meters. After solving this equation for height, the result is going to be 708,559.05 meters. Don't forget to subscribe and turn on the notifications in order to be updated about my new videos.